In this video, we are going to talk about phasors and phasor diagrams and discuss how useful it is when analyzing circuits powered with AC sources. The figure shows a series RLC circuit that is powered by an AC source. If we use Kirchhoff's voltage rule and sum the voltages around the loop, we get Vs is equal to VR plus Vc plus VL, where Vs, VR, Vc, and VL are the source, resistor, capacitor, and inductor voltages respectively. The source voltage is sinusoidal, which also produces a sinusoidal current of the form I of t is equal to I sub m sine omega t. In the figure, the current goes around the loop in the clockwise direction. Typically, the source voltage is known and is given by its amplitude and the frequency of oscillation. The resistance, capacitance, and inductance are also known. What we would like to know are VR, VL, VC, and the sinusoidal current. The voltage rule gives us a differential equation as shown after plugging in known expressions for VR, VC, and VL. The resulting differential equation is a non-homogeneous differential equation with a sinusoidal driving function. To solve this equation, you first need to determine the charge Q from which we determine the capacitor voltage. The next step is to differentiate the charge Q with respect to time to get the expression for the current, which then provides us with the expression for the resistor voltage. Finally, we differentiate the current with respect to time and multiply by the inductance L to get the inductor voltage. However, this is a very tedious process, especially considering that the general solution may be broken down into three types depending on the values of R, L, and C. A much simpler way to analyze the series RLC circuit is through the concept of phasors. Phasors is an alternative way of representing the amplitude, frequency, and phase of a sinusoidal function. The function is represented by projecting its amplitude to a circle with constant radius. The radius of the circle corresponds to the maximum amplitude of the function. An arrow is used to represent this maximum amplitude. We call this arrow the phasor. The phasor goes around the circle in the same way that the amplitude of the sinusoidal function changes. Let's say we have a sinusoidal function of the form as shown, that is, a of t is equal to a sub m sine omega t plus phi, where a sub m is the amplitude of the sine function, omega is the angular frequency, and equal to 2 pi times the frequency, and phi is the phase angle. In the simplest case, when the phase angle is 0, the sinusoidal function is 0, 180, and 360 degrees, has positive maximum amplitude at 90 degrees and negative maximum amplitude at 270 degrees. The phasor representing the sinusoidal function at 0 degrees is the arrow at the 0 degree angle in the circle. If we project that arrow to the y-axis of the sinusoid in the time domain, the projection is 0. The phasors at 180 and 360 degrees also have 0 projection in the sinusoidal waveform. The phasor at 90 degrees is now shown, as well as its projection in the sinusoidal waveform. At 270 degrees, we have this relation between the phasor and its waveform in the time domain. We can just as easily get the phasors at the other angles. This short video hopefully will help you gain an even better understanding of what phasors are and what they represent. The blue arrow is the phasor, while the red arrow in the left figure and in the right figure represent the projection of the sinusoidal waveform for various angles. These phasors represent the voltage or current of any circuit element. Thus, in the series RLC circuit, there is one phasor representing the current, another representing the resistor, another representing the resistor voltage, another for the capacitor voltage, another for the inductor voltage, and one more for the source voltage. The phasor diagram that you see in the current slide is actually called an argon diagram. It's a method of plotting complex numbers. A complex number has two components, the real component and an imaginary component, typically written like this. Z is the complex number, 6 is the real component, and 4 is the imaginary component. The small letter j represents the imaginary component and is equal to the square root of -1. Sometimes the small letter I is used. Thus, to plot this complex number, you draw an arrow with 6 units length along the real axis and another arrow with 4 unit lengths along the imaginary axis. The resultant is your complex number or your phasor. To get the magnitude of the complex number, we simply take the square root of the sum of the square of the real component and the imaginary component. You can get the angle by simply taking the tangent inverse of 4/6, because in the figure, the 4 unit length is the opposite side of the angle and the 6 unit length is the adjacent side of the angle. Now that we understand what a phasor is, let's take a look at the phase relationship between each circuit element. First of all, if the current I of t has a frequency of omega, then all circuit elements should have the same frequency. There is no reason for any of the circuit elements to have a different frequency unless that circuit element has its own driving frequency that affects the frequency of the source. If we consider a phase angle of 0 degrees, then the phasor for the current may be represented by the purple curve in the figure. The voltage across the resistor, represented by the blue curve, should have the same phase as the current. In other words, if the phase of the current is 0 degrees, then the phase of the resistor voltage is also 0 degrees. We know this because as the current increases, the resistor voltage also increases at the same time. The inductor voltage, on the other hand, has a phase that is 90 degrees ahead of the current. As the current changes with time, an inductor voltage is induced, consistent with Faraday's law. A small change in the current induces a small change in the inductor voltage, and a large change in the current induces a large inductor voltage. Thus, at theta equals 0, the change in the current is largest, and therefore the inductor voltage is maximum. Mathematically, the inductor voltage is proportional to the derivative of the current with respect to time. Thus, if the current is Im sine omega t, then taking its derivative will give us Lim omega cosine omega t. But cosine omega t is just sine omega t plus 90 degrees, as you very well know from trigonometry. Mathematically, this means that the inductor voltage is out of phase and ahead of the current by 90 degrees. The capacitor voltage has a phase that is 90 degrees behind the current. As the current changes with time, capacitor voltage changes as well. When the current is maximum, the charges across the capacitor begin to increase in number. Thus, the voltage across the capacitor also increases. As the number of charges increase on the capacitor plates, the capacitor voltage increases further. However, the current decreases because the charges remain on the capacitor plates. When the capacitor voltage is maximum, the capacitor is fully charged and there is no longer any current. Thus, at theta equal to 0, when the current is maximum, the capacitor voltage just begins to increase. Once the capacitor voltage is maximum, the current becomes 0. Mathematically, the capacitor voltage is proportional to the charge Q. Taking the derivative of the capacitor voltage with respect to time, we also get the derivative of the charge with respect to time, which is just the current. If the current is sine omega t, then integrating will give us negative cosine omega t divided by omega. But negative cosine omega t is just sine omega t minus 90 degrees, as you very well know from trigonometry. Mathematically, this means that the capacitor voltage is out of phase and lags the current by 90 degrees. Combining everything we've learned so far, we can now draw the phasor diagram for the current and the voltages across each circuit element. If we consider a phase angle of 0 degrees, then the phasor for the current may be represented by the purple arrow in the figure. The phasor for the resistor voltage can be represented by the blue arrow in the first figure. You can see that the phasors for the current and the resistor voltage coincide with each other regardless of the phase angle. It is plotted on the real axis. The inductor voltage, on the other hand, has a phase that is 90 degrees ahead of the current. It is also plotted on the imaginary axis. Regardless of the phase angle, the inductor voltage always leads the current by 90 degrees. The capacitor voltage has a phase that is 90 degrees behind the current. Regardless of the phase angle, the capacitor voltage always lags the current by 90 degrees. It is also plotted on the imaginary axis. What about the source voltage? This is the advantage of using phasors in analyzing circuits powered by AC sources. Phasors have two components, its magnitude and its direction. You can therefore treat phasors the same way as you treat vectors. You sum all the voltages in phasors the same as you sum vectors. Thus, in a series RLC circuit, the total voltage is the sum of the squares of the voltages of each of the circuit elements, and this sum is equal to the source voltage. From that, we obtain the amplitude of the source voltage. What about the phase angle of the source voltage? Since the phasor for the capacitor voltage and inductor voltage are 180 degrees out of phase, the sum of these two voltages is just VL minus VC. Thus, we can rewrite the expression for the source voltage to that shown. We can then determine the phase angle to be the angle between the phasor describing the sum of the capacitor and the inductor voltages, and the phasor describing the resistor voltage. The phase angle is then the inverse tangent of VL minus VC divided by VR. We can see from this equation that the source voltage does not have necessarily the same phase angle as the current and will depend on the values of the circuit elements. In reality, we typically set the source voltage as zero phase, and the phase angles of the current and the phasors of each circuit elements are computed relative to the phase angle of the source voltage. Graphically, we would add the phasors the same way we add vectors. That is, we either draw the resultant phasor from the parallelogram method, or we connect all phasors head to tail, and the resulting phasor would be the phasor corresponding to the source voltage. Again, the reason for using this and not simply using simple algebraic addition or subtraction is because the phasors are always expressed in terms of the amplitude and the phase angle of the phasor, and that phasors are complex numbers. If we divide everything by the current, we have the following expression, where Z is called the impedance. Z is called the source impedance, while ZR, ZL, and ZC are the impedances of the resistor, inductor, and capacitor respectively. These impedances are defined in terms of the resistance, inductance, and capacitance as shown in the table. ZR is equal to R, ZL is equal to J omega L, and ZC is equal to 1 over J omega C. R we know as the resistance. The small letter J is the imaginary number equal to the square root of -1. Omega L is called the inductive reactance, while 1 over omega C is called the capacitive reactance. The resistance is also in phase with the current. The inductive reactance is out of phase and leads the current by 90 degrees. The capacitive reactance is out of phase and lags the current by 90 degrees. Based on what we know about complex number, the phasor representing the total impedance can then be written as shown. Let's try to solve this problem. A series RLC circuit containing a resistance of 12 ohms, an inductance of 0.15 Henry, and a capacitance of 100 microfarad are connected in series across a 100 volt, 50 Hz power supply. Calculate the total circuit impedance, the circuit's current, power factor, and draw the voltage phasor diagram. At this point, we won't be able to solve the power factor just yet. We'll go back to solving the power factor after we've discussed the lesson on power in AC circuits. So, the given are the voltage source with a frequency of 50 Hz, the resistance of 12 ohms, the inductance of 0.15 Henry, and the capacitance of 100 microfarad. We are tasked to solve the total circuit impedance, the circuit current, and in order to draw the voltage phasor diagram, we also need to solve for the voltage across each of these circuit elements. So let's begin with the circuit impedance. Okay, the first thing that we can solve from here is the angular frequency, which is equal to 2 pi f. This is equal to 100 pi hertz. Okay. The next thing we will be able to solve is the inductive reactance. Inductive reactance is equal to omega L, okay, which is equal to 100 pi hertz times the inductance of 0.15 Henry. It's equal to 47.1 ohm. The next is the capacitive reactance, which is equal to 1 over omega C. So, plugging in the known values of 100 pi hertz for the frequency, angular frequency, and 100 times 10 to the minus 6 farad, we get 31.8 ohms. Now the impedance is given by Z equal to the square root of R squared plus XL minus XC quantity squared. Plugging in the known values, we get 12 ohm squared plus 47.1 ohm minus 31.8 ohm quantity squared, and taking the square root of that, we get for the impedance the value of 19.4 ohms. From this, we can also solve for the phase angle. The phase angle is given by the inverse tangent of XL minus XC over R, which is equal to tangent inverse of 47.1 ohm minus 31.8 ohms divided by 12 ohms. Okay, this has a value of 0.9055 radians or 51.9 degrees. So this this means that the inductor leads the current and that this circuit is mostly inductive. Well, this is true because we can see here that inductive reactance has a greater value than the capacitive reactance. Okay, now we can solve for the current. The current is easily solved from this equation, V sub S over the impedance. Since V sub S is 100 volts and the impedance is 19.4 ohms, the current or the magnitude of the current is 5.1 amperes. We can now solve for the voltage across each of the circuit elements. The voltage across the resistor is easily solved from the equation I times R, which is equal to 5.1 amperes times 12 ohms or 61.2 volts. The voltage across the inductor is easily solved from I times X sub L or 5.1 amperes times 47.1 ohm, which is equal to 240 volts. And finally, the voltage across the capacitor is I times the capacitive reactance, which is equal to 5.1 amperes times 31.8 ohms, or 162 volts. If you write down the waveform for the current, the resistor voltage, the inductor voltage, and the capacitor voltage, and the source voltage, we get the following. For the current, we have I is equal to 5.1 amperes times sine times 100 pi, this is omega, and then T. Okay. For the voltage across the resistor, we have 61.2 volts times sine 100 pi T. Okay. We know that there's no phase difference between the current and the voltage across the resistor. For the voltage across the inductor, we have 240 volts sine 100 pi T plus pi over 2. Okay, since the inductor voltage leads the current by 90 degrees. For the capacitor voltage, we have 162 volts sine 100 pi T minus pi over 2, since we know that the capacitor voltage lags the current by 90 degrees. Finally, for the source voltage, we have 100 volts times sine of 100 pi T plus the phase angle, which is 0.91 radians. We can now draw the phase plot or the phase diagram, and if you wish, we can also draw the sinusoidal waveform. So, by using MATLAB, I was able to program and type in the equations that I needed in order to make the sinusoidal plot and the voltage phasor diagram. In the sinusoidal plot, we have the current as this black curve, the resistor this blue curve, and you see that the current and the resistor in phase. The inductor, which is the red curve, leads the current by 90 degrees. The capacitor, which is this magenta curve, lags the current by 90 degrees. And the source is shifted by 51 degrees. We can also see this in the voltage phasor diagram. The current, which is hardly shown here because it's behind the resistor, well, it's behind the resistor because they are in phase. The inductor has this magnitude and direction, or phase angle. The capacitor also has this magnitude and phase angle. Okay, the inductor is 90 degrees ahead of the current, and the capacitive reactance, or the voltage across the capacitor, is lagging by 90 degrees with respect to the current, and the source is about 51 degrees with respect to the current. In this video, we are going to talk about utilizing the phasors for the parallel RLC circuit with an AC source. The figure shows a parallel RLC circuit with a voltage source. The voltage source drives the source current, which then divides at the junction into the resistor current, the inductor current, and the capacitor current. As previously discussed, the resistor current is in phase with the source current. The inductor current is out of phase with the source current and leads by 90 degrees. Again, the reason is that as the voltage is induced in order to oppose the change in the magnitude of the magnetic field, due to the incident current. The inductor voltage is in phase with the inductor current and leads the source current by 90 degrees. The capacitor current is also out of phase with the source current and lags by 90 degrees. As we previously learned, as the current increases through the capacitor, charges accumulate at the plates and the capacitor voltage increases. The current decreases as more and more charges fill up the plates and the capacitor voltage decreases. The capacitor voltage is in phase with the capacitor current. We use Kirchhoff's junction rule to sum up the currents. However, since phasors are composed of both amplitude and phase angle, the currents add up in squares as shown. Since the inductor and capacitor currents are out of phase by 180 degrees, we rewrite the expression as shown. The phase angle is similarly computed as in the previous lesson, but now in terms of the currents. It will then be elementary to solve for the resistor, inductor, and capacitor voltages. If we rewrite the derived expression for the current in terms of the voltage and impedances, we get the following expression. Since all voltages are equal to the source voltage in the given circuit, we are left with the expression as shown. Plugging in the resistance and reactances, we get the following equation. We now define new parameters that should make things easier to analyze the parallel RLC circuit. These are the admittance, conductance, inductive susceptance, and capacitive susceptance. We can then write the following expressions for these new parameters as shown. Now that we have computed for the phasor magnitudes, let's see how the phase angles are related for these reciprocal parameters. We know that in series RLC circuit, the phase angle is computed in terms of the impedances. Note that we can graphically represent tangent theta in terms of a triangle where the hypotenuse is the total impedance, the adjacent side is the resistance, and the opposite side is the reactance, and the phase angle is between the impedance and the resistance. In the parallel RLC circuit, we have the admittance expression given by the equation as shown. By inspection or comparison, we obtain the expression for the phase angle to be equal to the given expression with a negative sign. This negative sign is due to the fact that when we take the reciprocal of the reactances, the imaginary number becomes negative since 1 over j equals negative j. We can then depict the admittance triangle as shown, where the hypotenuse is the admittance, the adjacent side is the conductance, the opposite side is the susceptance, and the phase angle to be between the admittance and the conductance. Now let's talk about this problem. And this problem requires us to find the total impedance of the given circuit. The circuit consists of a source voltage with an amplitude of 5 volts and a frequency of 12 kilohertz, and a resistor, an inductor, and a capacitor which are arranged in parallel. The value of the resistor is 100 ohms, the value of the inductor is 15 millihenry, and the value of the capacitance is 0.022 microfarad. So there seems to be some sort of error in the typing, so that's supposed to be microfarad. Okay, now even though it requires us to solve for the total impedance only, as an exercise, we'll extend our solution to solving not just the impedance, but as well as the phase angle, the amplitudes of the current, and we're also going to plot the waveforms for the current and the phasor diagram for the current. Why are we plotting the current instead of the voltage? Well, first of all, the voltage across each of these circuit elements are the same, so it does not provide as useful information if we plot the current instead, because with the currents we also get the magnitude, but if we just plot the voltage, then all magnitudes are the same and we just get the relationship of the phase angles relative to each other. So it's better in parallel circuits such as these, it's better to plot the phase, the currents for the circuit. Okay, let's begin. So we have the given values, as we mentioned before. We can easily solve for the other given quantities as the following. Omega is equal to 2 pi f, which is equal to 24,000 pi hertz. Okay, I didn't bother to write down the actual number because I'm going to put this in MATLAB anyway to make the calculations faster and easier. The conductance, which is the reciprocal of the resistance, is equal to 0.010, and the unit for the conductance is Siemens, or sometimes we write it as just S. So just for comparison, I'm going to write this as millisiemens. For the inductive susceptance, which is the reciprocal of the inductive reactance, which is equal to 1 over omega L, we solve it as 8.84 times 10 to the minus 4 Siemens, or 0.88 millisiemens. And for the capacitive susceptance, which is equal to omega times C, this is easily solved as 0.017 Siemens, or 1.7 millisiemens. Okay, now it's probably clearer now why I wrote this in millisiemens, because it's easier to compare between the susceptance and the conductance. We see the conductance has the largest value, while the susceptance has about 1.7 and 0.88 for the capacitive and the inductive susceptances. And since these two susceptances are 180 degrees out of phase, these values will cancel each other out. We see that the capacitive susceptance is greater than the inductive susceptance, which means that this parallel circuit is more capacitive than inductive. We also expect that the phase angle will be at the first quadrant. Okay, let's take a look if that's correct. So the admittance we can easily solve by simply taking the root of the square root of g squared plus b sub l minus bc squared. Okay, plugging in the values, we get approximately 10 millisiemens. Okay, this is understandable because these two values here is just about less than or approximately 10% of the conductance. Okay, and if you take the difference between them, that's even smaller than 10%, which means that the conductance has the greatest contribution among the three. And solving for the phase angle, we get negative BL minus BC over G, and the value in degrees is 4.43 degrees. Okay, again, we expect this to be small because the difference between these two is much smaller compared to the value of the conductance. Okay, let's solve for the amplitudes of the current. Let's solve for the amplitude of the current source first. So this will be V times Y. Okay, now why is this like this? Okay, remember that if you recall, V is equal to IR, but since we're using conductance here, or the reciprocal of the resistance, then this will become I is equal to V times G. So it's the same also for the admittance and also for the susceptance. This will be then equal to 5 volts times 10 millisiemens, which is approximately 0.0501 amperes for the resistance, this is equal to V times G, 5 volts times 10 millisiemens, which is approximately again 0.0500 amperes. So it's just a very small difference. Then if we continue on to the current across the inductor, we have V times B sub L, 5 volts, 0.88 millisiemens. That's about 0.044 amperes. And then I C naught is equal to V times BC is equal to 5 volts times 1.7 millisiemens, which is about 0.0083 amperes. Okay, so we can make a plot of the source current to be equal to to this expression, which includes the phase angle, the plot for the resistor current, which is equal to this expression. We assume that the phase angle is relative to the resistance. IL is equal to IL naught sine omega t plus 90 degrees, and then IC is equal to IC naught sine omega t minus 90 degrees. Okay, one last thing. We're asked for the total impedance, and the total impedance is just the reciprocal of the admittance. And if we solve for that, this is about 99.7 ohms. Okay. The next step is to graph these values. So here we have in the right image, we have the phase diagram for the currents, and in the left image we have the phase diagram for the sinusoidal waveforms. We see that the contribution from the inductor and the capacitor is much smaller compared to the contribution from the resistor. So most of the source current comes from the resistor, and that is why the angle between the source current and the resistor is it's small, but it's not very small. We can also see that in the sinusoidal waveform there's a small shift, which again corresponds to about 43 degrees, which is the phase angle. The shift between the resistor and the source current. And we can see here that the shift between the inductor and the capacitor is 180 degrees, and the shift between the inductor between the resistor is 90, with the inductor leading, and the shift between the capacitor and the resistor is 90 with the resistor leading.
In this video, we are going to talk power in circuits with an AC source. The basic definition of power is the product of the current and the voltage. We generalize this and add a phase difference between the current and the voltage. We then write as shown. We then use the trigonometric relation shown and define phi as the difference between phi I and phi v. We then obtain a new equation as shown. This power is not possible to measure with a simple multimeter. If we then solve for the average power, the second term with the time component vanishes, since the average of cosine over time for all time is 0. We are then left with the expression for the average power to be equal to I naught V naught over 2 times cosine of phi. In a purely resistive circuit, the average power is then equal to the top equation, since there is no phase difference between the voltage across and currents through the resistor. In a purely capacitive or inductive circuit, there is no average power.
Thus, both the capacitor and inductor do not consume or dissipate any real or true power. Taking a look at the graph, where both the voltage and the current are in phase, power is always used up, and there is no power returning to the resistor. However, the inductor and capacitor do dissipate an imaginary power, and we'll understand this a bit better in a little while. First, let's take a look at the second term in this equation. This is an equation which we derived earlier. In an inductor, the phase difference between the voltage and the current is positive 90 degrees. Thus, if we set phi I to be 0, phi V should be 90 degrees. First term vanishes because phi I minus phi V is 90 and cosine 90 is 0, while the second term becomes as shown. Taking the average power of this, we obtain the expression as shown. What does this power mean? If we take a look at the figure, we see that the voltage and current waveforms are out of phase by 90 degrees and the voltage leads the current. If we multiply these two results, we have the shaded waveform for the instantaneous power. Notice that between the angles 0 and 90 degrees and 180 and 270 degrees, the power is negative, while between the angles 90 and 180 degrees and 270 and 360 degrees, the power is positive. Thus, you can see that the power is being used up and then returned alternately. Thus, power is moved back and forth through the inductor, and therefore it's not really used up. In one full cycle, the total power used up is just 0. The magnitude 1/2 I naught V naught is just the average of the absolute value of the power. This is the amount of power that is being exchanged. If we consider capacitive power, then the phase difference is negative 90 degrees between the voltage and the current, with the voltage lagging as shown in the figure. Then we obtain the following expression as shown. The negative sign only indicates that the orientation of the sine function. Again, the power alternates between consumption between 0 and 90 degrees and 180 and 270 degrees, and replenishment between 90 and 180 degrees and 270 and 360 degrees. There is no power that is used up, but only power that is exchanged back and forth in the capacitor. In one full cycle, the total power used up is just 0. The magnitude 1/2 I naught V naught is just the average of the absolute value of the power. This is the amount of power that is being exchanged. We can now summarize power in AC circuits. For real power, we have the following expression. For reactive power in a pure inductor, we also have the following expression. For reactive power in a pure capacitor, we again have the following expression. Typically, the real power has units of watts, and the reactive powers has units of volt amperes. There's one more type of power called the apparent power, which combines both the real and reactive powers. The equation is shown. We can draw a power triangle for the AC circuit. The ratio of the real power to the apparent power is called the power factor. As you can see, the power factor can be anywhere between 0 and 1. If the power factor is 0, then there is no real component, and the AC circuit is either capacitive or inductive, depending on which power component is larger. If the power factor is 1, then there are no imaginary components of power, and the power is solely due to the resistor consumption. If the power factor has a value between 0 and 1, then if it is more inductive, the power factor is said to be lagging, since the real power lags the reactive power. Otherwise, if it is more capacitive, then the power factor is said to be leading, since the real power leads the reactive power.
Let's apply what we've learned about powers in AC circuits using the two circuits that we've used before, the series circuit and the parallel RLC circuit. Let's begin with the series RLC circuit. If you recall, we have this solution for the series RLC circuit where we were able to solve for the impedance, the voltages across each circuit element, and the current, and also the phase angle. We were also able to determine the function for the current, the resistor voltage, the inductor voltage, capacitor voltage, and the source voltage, from which now we can determine the power across the resistor, or the power dissipated by the resistor, the power across the inductor, the power across the capacitor, and the power in the source, power provided by the source, and also the power factor. So those parameters are easily solved by simply using the following equations. For the source, we know that we can use I, the current I, times V sub S. For the power across the resistor, the power dissipated by the resistor, it's I times V sub R. For the power across the inductor, it's I times V sub L. The power in the capacitor, it's I times V times C. And of course, for the power factor, that's easily solved to be the real power divided by the apparent power. Okay, so if we use again, it's easier to use tools that are already available, such as MATLAB. And by using MATLAB, I was able to draw this power triangle where you should see the real component of the power shown as the blue phasor, the reactive power shown as the magenta phasor in magenta, and the apparent power shown as the green phasor. Okay, and from there we were able to compute for the power factor to be equal to 0.76. Okay, in the upper right figure, you'll see the curve for the current, the waveform for the current, the voltage, and the power. The power curve was obtained by simply multiplying the sinusoidal waveform between the current and the voltage. The y-axis is in watts, so it displays only the units of the power, but the scale is the same for the voltage. You just use units of volts. And for the current, the scale is multiplied by 10 because the current is actually 10 times smaller than this. The x-axis is, of course, theta. And you see in this curve that the waveform for the power is purely dissipative. It's only along the positive y-axis. If we compute for the magnitude based on the values that we've used before, so for the power across the resistor, we have 5.1 amperes. That's the current that we computed before. And the voltage across the resistor is 61.2 volts. This is the actual amplitude. Okay, and since if we do the mathematics, this is 312 watts. But if you look at the figure, the power is actually approximately 317 watts, which is about the same, probably just due to some rounding off error. In the upper right figure, you see the power in the inductor. You see that the current again is scaled by 10 and the voltage is scaled by 1. And the power you obtain by multiplying the current and the voltage waveforms. The current is out of phase with the voltage by 90 degrees, with the voltage across the inductor leading the current. And you can see these alternating power from the positive
to the negative, to the positive, to the negative, meaning that it's consuming power and then it's returning power, and then it's consuming it again and it's returning power. And that's for an ideal inductor. If we do the mathematics, if you recall, the values that we obtained for the current is 5.1 amperes, and for the inductor, it's 240 volts. Okay, this will give us around 1224 volts ampere, but in the figure, okay, you can clearly see that it's not 1000 to 1.2 kilovolt amperes, but it's about 312 watts. And the reason for this again is because there's a shift. So the amplitude of the maxima of both the current and the voltage are not in phase, and therefore the maximum amplitude occurs only at these angles where the current and the voltage where the current and the voltages do not have their maximum values. Okay, what about the lower left figure? The lower left figure shows the capacitor. So again, we can obtain the power in the capacitor based on the values we've computed before. This is equal to 826 volt amperes. But again, in the figure, if you look at the figure, then this is about 421 watts. Again, the reason for this is that the voltage and the current are out of phase by 90 degrees. So the maximum of these values occur when the current and the voltage, well, they're not at their maximum. Okay. And finally, for the source, or for the apparent power, we have 5.1 amperes times 100 volts, which is the given quantity. This is about 510 watts. But in the figure, we have about 416 watts. Okay. Now, in this figure, the current and the voltage are out of phase by 51.9 or 52 degrees. Okay, and since they are out of phase, the power that is dissipated, or power that is provided by the source also has a dissipative component and a return component. The return component is actually the difference between the reactive power in the inductor and in the capacitor, and that's a result of the of taking the difference between the inductor and the capacitor reactances. Okay, and you notice also that there's more dissipative power compared to the return power. The return power is naturally coming from the interaction between the inductor and the capacitor, and the dissipative power mostly comes from the resistor, but because the inductor and the capacitor are also trying to get as much power as they want, okay, so there's some sort of there's some balance that they have to achieve. So there's also some dissipation that is occurring between the exchange. Okay, now let's take a look at the parallel series circuit example. If you recall that in this example, we have a voltage source of 5 volts and a frequency of 12 kilohertz, and a resistance of 100 ohms, an inductance of 15 millihenry, and a capacitance of 0.022 microfarad. We've already solved these quantities before. the conductance, the susceptances, and the admittance, and also got the currents, and also finally got the impedances. Okay, and from there we were able to graph the phasor diagram and the sinusoidal waveform. Okay. Okay, now again using MATLAB we can solve for the power across each of the circuit elements, and the power across the resistor, the real power across the resistor, is shown in the in the lower right box. If we try to solve for the power across the resistor, then we have 5 volts times the current, which we already solved before, to be 0.0500 amperes, and that is equals to 0.2500 watts. And in the figure we have the power to be equal to 0.2500 watts. Okay, and for the inductor, the power is obtained by multiplying 5 volts by 0.044 amperes. Okay, this gives us 0.0221 watts, but in the figure, this power is seen to be 0.0111 volt amperes. Okay, and for the capacitor, we have 5 volts times 0.0083 amperes, which gives us 0.0415 watts or volt amperes. In the figure, we have 0.0207 volt amperes, and for the source, this is equal to 5 volts times the current of 0.0501 amperes, which gives us 0.2507 watts, and in the figure it's just 0.2500 watts. Okay. Notice that in the figures, the current is multiplied by 100, as well as the power. So they are scaled to 100 in the reactive power in the capacitor and in the inductor, but in the apparent power and real power, they're scaled to about 10. Okay, so what you see there are exaggerated graphs of the power and the current. Okay, and we have these values, and we can already explain the discrepancies between these values. These values that were initially computed were just based on the maximum amplitude of the voltage and the currents, but these values that were computed next and seen in the figure were values obtained when multiplying the two waveforms by each other. Okay, and the difference and the discrepancies arise because they are because the curves due to the reactances are out of phase. Okay, so if we go now to the power triangle, this is what it looks like. Okay, we have the real power for which we obtained from the power across the resistor, and the reactive power, and the apparent power, and here the power factor is approximately equal to 1. You notice also that the reactive power is scaled by 100, so that means that the angle is very, very small. It's actually 4 degrees, and this results to a ratio of the real power and the apparent power that is approximately equal to 1, or in this case, if we round them off, then we get a power factor of about 1.